Thank you. Hi, everyone. I'm Charles, and I'm going to be presenting in this talk my work on Twist, which is a quantum programming language for helping developers reason about entanglement in the programs they write. This is joint work with my collaborators Chris McNally, as well as Michael Carbon at MIT. Before I start, I just want to say for everyone who was here in the morning session, first of all, nice to see you again. Second of all, this work was actually presented initially a few months prior to the Tower talk. So if it feels a little bit like I'm going back in time, that's why. And also, since I have a slightly longer time slot, I decided to have a little bit more background about quantum introductory stuff for people who may find that useful. So without further ado, what is quantum programming? Well, one way of defining quantum programming is that it is the process of writing programs that perform the operations that quantum computers can perform on the quantum states that they store. So I have an example program here that encodes the protocol of quantum teleportation, which is a fairly well-known tool in quantum information science that transmits the information from one qubit to another. So this program is fairly reflective of a lot of quantum programs in that it has constructs for initializing qubits, which are the quantum equivalent of bits, executing operations known as unitary gates on these qubits, which are kind of the magic of most algorithms. And at the end of the program, some of the qubits are measured, which means that some classical information is obtained from the quantum state. And in the case of this particular function, some quantum state, the qubit Q3 at the end, is actually returned as the output of the function. So it turns out that the program that I wrote here that I called quantum teleportation actually has a little bit of a bug in it. To understand what that bug is, let's first talk about the specification for the teleportation function. Quantum teleportation, when given an input, here the qubit Q1, specifies that the output, which here is Q3, should wind up in the same quantum state as the input Q1. So for example, if I pass in the input, this uniform superposition of 0 and 1, I expect to have that same qubit as the output. Unfortunately, I do not. Actually, when I run this program, I observe that 50% of the time I get the right answer, and 50% of the time I get something which is close to but not quite the right answer. The difference is that there's this sign difference on the 0. It's a phase difference, which actually can be observed when somebody uses this qubit in the rest of the computation. So what is this bug? How can we find it? How can we fix it? Well, let's try to find some spots where it could have come from. We know that the operation of quantum measurement, by which you take a quantum state and observe and obtain some classical measurement outcome, we know that this action is probabilistic in nature. You get a probability distribution of outcomes. And that might explain why the bug also happens probabilistically. But there's something really weird, which is that in this program, I measured qubits Q1 and Q2. So they could be probabilistic, but why on earth is Q3 probabilistic at the end? And the reason, you already know from the title of this talk, is quantum entanglement. It's a rather strange phenomenon that can be summarized as saying that when you perform operations on parts of your program, for example, one of the qubits, these operations can actually affect the other qubits in your system as well. So in particular, what happened in this program is that right before we did that measurement, we have two qubits Q1 and Q3 that were entangled with each other. And when these two qubits are entangled, it means that if you measure one of those qubits, that measurement has an effect on the other qubit with which it is entangled. And this causes the bug. I'm just going to give away the answer here for now, which is that in order to fix the program, you would have needed to use a different unitary gate. In this case, you would use a controlled Z rotation as opposed to a controlled not rotation. If you do this, it actually causes the entanglement to be broken between Q1 and Q3, which means that when Q1 is measured, Q3 is not affected. So, why do we care about entanglement? Well, apart from it being present in this example of teleportation here, it has been proven that entanglement in some form is strictly necessary for us to obtain the kinds of quantum speedup that we see in algorithms such as Grover's algorithm for search or Shor's algorithm for factoring. And there's also been a lot of prior work showing that entanglement is actually very useful for thinking about the programs that you write. For example, it's really useful for debugging. It's useful for reasoning about when the temporary or ancilla qubits are safe to discard from your program. And there's also other uses such as analyzing the information content of information that can leak from the program, so there's some sort of privacy argument. And entanglement also comes into play for certain compiler optimizations. The problem that we seek to address in this work is that existing programming frameworks don't directly enable programmers to reason about entanglement at the level of the program and understand how entanglement affects the operations in their program. The solution we propose in this work is a language called Twist, which provides the first set of semantics for sound reasoning about entanglement using a semantic property we developed called purity. In a nutshell, this purity property simply asserts the absence of entanglement. And we'll see that the ability to actually quantify purity and check for its presence is going to be critical to reasoning about entanglement. So, to give you a lightning-fast overview of what Twist is, if we take a program like teleportation, Twist allows us to annotate the different pieces of data within the program as either being pure or mixed. A pure piece of data is one that is not allowed to be entangled with other pieces of data, whereas a mixed piece of data is. It's a relatively simple distinction. Twist also supports a set of operators that allow us to operate between these two classes of data. For example, there are assertions that allow us to assert a lack of entanglement between one piece of data and the rest of the program. The result of using these assertions in combination with Twist's static and dynamic program analyses allows us to show that a given quantum program satisfies a correctness specification that is specified by means of these pure and mixed annotations. So, let's first take a deeper dive into what entanglement is, as well as a little bit of an overview of quantum information for those of you who may not be as familiar. So the elementary unit of quantum computation and quantum information is the qubit. In the example program here, we actually utilize 3 qubits. There's the input Q1, as well as 2 qubits generated by the program. The definition of a qubit is it's just like a classical bit, except it can be more things. Right? Not only can it be the 0 state or the 1 state, but it can actually take on a superposition state where you put these complex amplitudes, gamma 0 and gamma 1, on the 0 and the 1, with only the condition that the norms of these complex amplitudes sum up to 1. You can think of it kind of like classical probability distributions, with the distinction that instead of having real valued probabilities that add up to 1, you have complex valued amplitudes whose norms add up to 1. So, generalizing a qubit, we can create something called a pure quantum state, which I'll just define as a superposition containing 1 or more qubits. So in this example here, we can say that the input of the program, the superposition of 0 and 1, is a pure state. And so is the state that is being produced by this helper function called bell pair. It's producing the state that's a superposition of 0, 0, and 1, 1 over 2 qubits. And it's also a pure state. Given 2 pure states, you can combine them to produce a larger pure state by taking the tensor product. So here, the tensor product of these 2 states is the state of the whole program. What can you do with quantum states? Well, you can execute unitary operations on them. So in this program here, we're executing a couple of unitaries, such as the controlled NOT gate, the Hadamard gate, and the controlled Z gate. For the purposes of this talk, it's not too essential to know the exact semantics of each one of these gates, but you do have to keep in mind that each gate has a unique semantics mapping from states to states. And of course, the final step is measurement, which is a probabilistic operation that collapses superpositions down to classical states. When you measure a superposition with some probability, you get one of the classical states stored in that superposition. Specifically, the results of a measurement can also be modeled as a state. We call it a mixed state, which here I'll just define as a probability distribution over pure states. So, whereas the input of our example was a pure state, the buggy output of our example is a mixed state. So, how do we define entanglement? One way to think of it is when the measurement outcome of one of the qubits of your system is able to determine the state of another. And what I mean by this is, let's take this state right here. It's a superposition of 0, 1, and 1, 1. What happens to this state if we measure the first qubit? Well, we get one of the outcomes in the superposition with probability 1/2 each here. So you get either 0, 1, or 1, 1. And the important thing to note is that the outcome of the second qubit is always 1. So in some sense, it's not being impacted by the measurement outcome of the first qubit, whether it was 0 or 1. So a state like this we're going to call separable. Separable meaning not entangled. By contrast, let's think about this bell pair state we saw a few slides ago. What happens when you measure this qubit? Well, something similar. You get either 0, 0 or 1, 1. But now look what's happened. The state of the second qubit you get in the final output is determined by the measurement outcome of the first one. So we call this entanglement, and this is an entangled state. All right, so that's one way of understanding entanglement. Here's another one if it helps. An entangled state is a state that you can't write as the tensor product of two smaller pure states. So here you can see the separable state here. Both of the branches of the superposition, they had that 1 in the second position. So you might as well just factor it out and say it's a tensor product of a 0 plus 1 and a 1. Whereas with the entangled state, you can't do this. That's the hallmark of entanglement. You cannot write it as a tensor product of smaller states. Cool. So let's talk then about how Twist solves the problem of reasoning about entanglement in the programs that a developer writes, and how the concept of purity comes into this. Revisiting the bug a little bit, recall our problem was that we had a pure state as input and a mixed state as output. How might we try to catch this bug? Well, here's the observation that we can make. At the end of the program, we expected that Q3 should have been a pure qubit. That was the specification of teleportation. For some reason, it wound up as a mixed state anyways. So why don't we just enforce this property? Let's enforce the property that Q3 is not supposed to be entangled with the qubits that get measured during the execution of the function. So this is a property that we formalize as purity. Now in the paper, we give long operational and denotational definitions of what exactly purity means. I'll spare you the details and just summarize it as saying, you can say that an expression is a pure expression under a given quantum state of the program if it is the case that the expression evaluates to a unique final value v here, and the program state also evolves to a unique final state. And furthermore, the qubits that wind up in this final value are separable from the rest of the final state. Okay, so this is a formal definition. Let's try to give some intuition to it using the example again. So we're going to do that by analyzing how Twist actually incorporates purity into the type system, the assertion operators, and the verification analyses. So what we can see from this example is that every single qubit in the program has been annotated with an annotation describing whether the purity property is supposed to hold on it. And remember that an intuitive explanation of purity is that it is not supposed to be entangled with any other data in the program. So here we see that we have the buggy teleportation function. The buggy teleportation function takes in a pure qubit and outputs, somewhat mysteriously, a mixed qubit. That's what's going to allow us to determine that something about the specification of teleportation has not been satisfied. The way that we derive that the output of the function has mixed type is by pushing through all of the type rules, right, through the program, such that type checking the program is, in some sense, sufficient. So yeah, like I just said, the actual specification of teleport expects this output to be pure rather than mixed. So how do these typing rules work? Well, Twist introduces the concept of an entangled pair of pieces of data. So it's kind of like an ordinary product type, except that it additionally stipulates that the two halves of the pair are permitted to be entangled with each other. And that's denoted using this ampersand type operator. So in this example, Q23 is a pair of qubits that is permitted to have entanglement between them. Now, what does it mean for there to be entanglement between them? Well, it means that if you then go ahead and project out the two halves of the pair, now we have to annotate the elements as being mixed. And if you follow this reasoning all the way through, you realize that by the end of the function, Q3 is going to have mixed type because it came from this entangled pair. Cool, so let's go ahead and actually fix the bug now. So recall that a way of fixing the bug is replacing the C0 gate with a CZ gate. And we know that the semantics of the gate are supposed to get rid of the entanglement. How can we get the type system then to accept the program? And how can we be assured that the program actually has that nice pure type in the return type? What we do is, first thing here is we create an entangled triple of all three qubits in the system here. Right, entangled triple, because at this point in the program, Q1, Q2, Q3, all of them may be entangled with each other. And the next thing that we do is we're going to actually specify, no, I know more than that. I actually know that, first of all, the three qubits that I'm dealing with, these three that I'm holding on to, when interpreted together, they are not entangled with any other part of the universe. Right? The three of them constitute a pure entangled pair, or triple in this case, rather. The next thing that we're going to do is we're going to say, I actually know even more than that. I know that the first two qubits are separable from the third. So you see here that we've used two operators in Twist. We've used the cast operator, which allows you to say that a given piece of data in your program is pure, unentangled with anything else. And we've used the split operator, which, given an entangled pair of two things, allows you to say these two things are actually separable from each other. You might be wondering why we need two separate assertion operators, and I will be getting to that shortly. After we use these assertions, well, we still need to make sure that the assertions have been used correctly. You can't just throw cast and split willy-nilly and expect our reasoning to be sound, after all. The way that we're going to do that is using a combination of static and dynamic analyses that are built into the Twist system. The first thing that happens is that Twist will automatically and statically verify that all of the cast operators you use in your program are sound. What this means is that, well, here's an example of how the static analysis works. We're going to start with the argument of that cast, and we're going to ask, well, what things could it possibly be entangled with? This is a relatively straightforward application of just backward logic, where we propagate the sources of information into this piece of data, and we trace backwards looking for any other qubits, any other data that these three could have been entangled with. Do we find any? Well, no, we only find entanglements between Q1, Q2, and Q3. We trace all the way back to, in this case, the input of the function and the output of del pair. And we know externally that these values are supposed to be pure. So at this point, it is safe for the static analysis to conclude that this value should actually be given pure type. So the next thing that happens is that Twist uses a dynamic runtime analysis to verify that the split operator is sound. How does this work? Well, we aren't really able to get a precise version of this analysis to work statically. So we have to check it at runtime. And specifically what we do is two approaches depending on whether the program is being run on a classical simulator, on classical hardware, or whether it is running on quantum hardware. And the details here are in the paper, but I'll briefly summarize it by saying this. Remember our definition that an entangled state is defined as a state that you can't write as the tensor product of two smaller pure states. That's exactly the property that we're going to exploit here. So if we have access to this runtime state on the left, the state of the program at the point where the split operator is being invoked, we're going to ask whether there is any way of factorizing it into two smaller states. If you're doing this in simulation, it turns out you have access to a full readout of the coefficients of the quantum state here. And it's just a matter of linear algebra. Specifically, you do a singular value decomposition, which relatively quickly tells you whether the vector is separable into a tensor product. Of course, doing things in simulation means you have to deal with exponentially large representations. So we also have a proposal for how to do it in hardware. In hardware, it turns out that there is a family of relatively lightweight testing approaches based on something called the iterated swap test that can actually be used to determine whether a state is separable or not. And I'll refer you to the paper for more theoretical details on this. So I'll finish off by talking about how we evaluated Twist, its performance in practice. We asked ourselves 3 research questions. The first one is, well, how expressive is this language that we've created? There are a number of languages that exist for quantum programming these days. Can we actually manage to express meaningful quantum algorithms in our new language? The next question is, well, how sound are the analyses that we have devised? Can we actually get the language to reject programs that contain bugs that are caused by a misspecification or a violation of purity? And the final question is, well, if we're doing all of this verification at runtime, what's the overhead going to be? So here are some of the results that we obtained for research question 1. And what I want to point out here is that first we implemented a number of algorithms in Twist, including Grover's algorithm, the quantum Fourier transform, error correcting codes. And we have shown that the Twist type checker, static analysis, and dynamic analysis actually accept these programs. So this is mostly a sanity check here, right? These programs are actually known to be valid. And what the columns in the middle are indicating here is, well, first, the valid column on the left, full of check marks, indicates the ground truth of whether these programs should be accepted by Twist. And on this slide, the answer is yes. The next column, the types column, is indicating whether the type system actually accepts this program. It's kind of like the first check we do, followed by the static analysis, which statically checks the cast operators, followed by the runtime analysis that checks the split operators. So something interesting that I will point out about these results here is that, well, Twist is sound and precise for all but one of the programs here, this teleport measure program, in which case you can see that the static analysis actually fails, meaning that the static analysis is overly conservative, but the dynamic analysis passes. And I'll come back later to what's going on with this test case. But for now, let's move on to the actual interesting invalid programs. So how do we get these guys? Well, we took the programs from the previous slide and we introduced a bug, one that we felt would be indicative of a realistic bug that could be introduced into a quantum program and might be difficult for a novice programmer to catch. So for example, these include things like having a program that does not uncompute a value correctly. It discards it into the environment, and basically what that means is that things become mixed states rather than pure states. There are other bugs here, such as the third example here, I'll just pick it out of random. What this bug is doing is, instead of generating the Bell state that we saw on the earlier slide, it generates this slight variant called a GHZ state and then drops one of the qubits, which looks kind of like a Bell state, but is not, in a rather subtle way that I don't have time to explain. The bottom line here is that we actually get that Twist is sound and precise on all of these examples. So the valid column being all X's means all the programs are supposed to be invalid, and as you can see, all the programs are in fact rejected at either the types, the static checking, or the dynamic checking. All right, how did we then benchmark the runtime overhead of the quantum programming language we designed? This is pretty hard. There don't really exist great benchmarks for interesting programs at relatively high levels of abstraction for quantum programming. We had to be a little bit creative here, and for performance purposes, we chose to evaluate this conditional modular multiplication operator, which is something that you might find, say, in Shor's algorithm. So what we did was we implemented a conditional modular multiplication on a range of 4 to 22 qubits to show some scalability. And the condition we want to check here using Twist's specifications is that if you run a conditional modular multiplication, and then you run that multiplication backwards again, then you should get back to where you started, which means that your condition qubit should be separable from your data qubits. Again, this is a relatively basic thing that you want to be true about your program. We can actually check that this property holds using a runtime purity assertion. So, of course, we're trying to evaluate the performance, but we don't have access to a quantum computer that can really robustly handle 22 qubits. So we evaluated it in simulation. We implemented Twist in a quantum simulator, and we computed the total runtime of these programs and the proportion of runtime that was spent actually checking these runtime verifications. So these are the results that we got. I mean, they are relatively preliminary in the world of quantum performance benchmarking. But the point that I want to point out about these results is that Twist's runtime verification, at least in simulation, have relatively low overhead. It's less than 3.5%. And the intuition here is it doesn't take very long to actually check that the state is separable at runtime. You might be wondering, why is it that as the number of qubits increases, the overhead ends up decreasing? The reason in our benchmarks is because the property that we wanted to check, which again is the condition qubit is separable from the data qubits, that can actually be checked using just one assertion, which means that as the number of qubits is going up, it's effectively amortizing out the cost of performing this verification. This may, of course, not generalize to other classes of programs, and we'd be interested in exploring more kinds of programs in the future. Okay, I promised I would tell you about this teleport measure program. So here it is. This is the program. Okay, I also have to point out what is so weird about this program. This program is a variation of that teleportation protocol we saw on the first slide, with the small difference that instead of doing extra quantum controlled operations, it's doing these classical operations where a qubit is being measured, and then the classical outcome of that measurement is being used to control the execution of the program at this point. This is a fairly sophisticated thing to do in a quantum program. And in Twist's case, it's rather unfortunate because what it requires us to do is use a less efficient mixed state simulator as opposed to a pure state simulator. A mixed state simulator basically has to store a much less compact representation of the quantum state. And executing the assertions on this less compact representation takes much longer. We did a little bit of a performance evaluation between the pure and the mixed state simulators. And as you can see, there's basically this quadratic drop-off. I mean, it's a log scale, so half the slope, basically, if you're using the pure as opposed to the mixed state simulator. So this is a performance argument for the difficulty of checking certain properties of quantum programs when mixed states get involved. And it also explains why the static analysis was imprecise earlier, because reasoning about pure states just doesn't cut it for certain classes of programs. Okay, so to briefly summarize, what we presented today was Twist, a language for sound reasoning about entanglement in quantum programs. We developed this semantic property called purity, which is really useful for thinking about entanglement. And we showed that purity can actually be baked into a system of types, assertion operators, and verification analyses on quantum programs. Before you go, I want to look forward a little bit. It's been a while since I actually, really worked on this particular project. And now that I'm presenting it here, I wanted to share some ongoing developments. So Twist involves a combination of these runtime checks, runtime verification, as well as static reasoning about programs. Is it possible to make these runtime verifications more expressive? Can we check arbitrary properties of quantum programs at runtime? This is, of course, a very hard question. There are, I think, other talks here and many papers being published every year on this exact subject. But in the context of what we're doing here, I speculate that we're in a little bit of a sweet spot between the expressiveness of what we can check using these purity specifications and verifications and the limit to what you actually can achieve in the context of quantum information. So what could we do to twist to make it better? There are so many things. We could make the annotations much richer. So we can say things like, not only are these things entangled, but they're entangled in this way. Or perhaps we could say, these two things are definitely entangled, as opposed to having this approximation of may possibly be entangled. These may be things that we want to do. But we also have to think about the other side, which is, well, how do we actually check these things? If we want to check them at runtime in any way, then we have to deal with the limitations of existing techniques. Swap tests, they're good at telling you whether the state is entangled, but they're questionable for being able to tell you more information. You could, of course, statically reason about the program to check these properties, but the scalability is then in question. And of course, keeping things in classical simulation is going to be intractable. So it seems like there's almost some sort of continuum here. On one end of the continuum, you have the process of performing full quantum state tomography on your program state. Tomography is a fancy word for saying, given a quantum state, actually given lots of copies of that same quantum state, you're going to keep measuring it in more and more interesting ways to try to recover a whole classical description of that quantum state. As you might imagine, in general, that takes exponential time in both time of running the process and the number of samples that you need. It's also a little bit hard to interpret the results. I mean, you have this exponential output of data, and you still don't necessarily know what you're looking at, even if you're staring at it. Of course, it does capture all of the potential information hidden in that quantum program. On the other end, you have something like what we did, a relatively cheap operation like a swap test that is pretty easy to interpret. In this case, it just tells you, is it separable or is it not? And there's good reason, unfortunately, to believe that it's still fundamentally limited how much this technique can tell you. Is there somewhere in the middle? Can we actually get something in between these extremes that shares some of the benefits of both sides? I think the speaker in the next talk should hopefully have a good amount to say about that. So, if you're interested in checking out our paper, it's available on Archive. Our artifact is also available on GitHub if you want to tinker around with it. And one of the messages that I'd like to leave you with here is, if we're going to be programming these quantum systems, we do need some way of making quantum concepts make sense, right? Taking things like entanglement and turning them from these very vague emergent properties about programs and baking them into how we think and write about programs directly. So let's find the abstractions to do that.
Okay, well, thanks very much for the talk, Charles. We have plenty of time for questions, so let's start with Dominique.
So I'm curious about what entanglement exactly means in the presence of measurements, because you had this measure teleport, and the way I understand entanglement, I would have thought in this case it is trivial that it's pure what you get out, because there are 3 potentially entangled qubits, 2 of them get measured, so the third one must be pure because there is no other candidate left to be entangled with, unless entanglement also means that it's not probabilistic correlated.
Yes, that's a fantastic question, and it's kind of what made this particular example so hard to reason about. It also shows how the little bit of intuition I gave on purity meaning lack of entanglement, how that intuition sometimes breaks down. When you have measurement in your program and you actually have different probabilistic outcomes that are merely classically correlated, these things are not entangled, but they're also not pure, right? So the definition we gave for purity is intended to capture, in some sense, not only entanglement, but classical probabilistic correlation.
Yeah, so if I would, for example, pick a random bit and then initialize a qubit, you would not call it pure.
That's right, we wouldn't call it pure.
Okay.
And if we wanted to do something like actually say that something is bona fide, genuine quantum entanglement, I mean, you saw it on my previous slide there, that would actually require some additional work.
Next one back.
So I don't know if you remember the example I had in my presentation. There was the situation that there's basically a quantum variable which is entangled with another quantum variable inside a function, and then the local variable is uncomputed, while the higher level quantum variable is still there. Would that be a situation where Twist would be able to recognize that the first quantum variable is not entangled to the local variable because it is uncomputed?
Right. So I think there's a bit of two questions that are going on there. The first one is about uncomputation and about Twist's ability to recognize when uncomputation has succeeded. So Twist doesn't really have what we might call automatic uncomputation and the ability to reason about that directly. You have to go at a slightly lower level and say, at this point, I, the developer, have implemented a bunch of things that are purported to uncompute this thing, and then I will use Twist's assertion operators to convert the type, and I will use Twist analyses to check that those operators actually worked correctly. So it is possible to be assured that the uncomputation was correct, but not as automatically as you might hope. The other question, I think, is a little bit more subtle, which is, well, what happens when two things are unentangled with each other, but they're both entangled with something else mysterious in the rest of the world? That's also very difficult to deal with, and we don't really have a great way of dealing with it right now.
All right, thank you.
Thank you. So I think initially I thought it was funny that you characterized Joscha Linden paper as entanglement is important, because I thought the conclusion of the paper was the opposite. That it's
really?
not entanglement specifically, because they actually emphasize entanglement, saying any representation that gets exponentials is necessary, but entanglement is not special. And they give the example of the Clifford gates and so on. So, but entanglement is, important in some sense, but it's not unique.
Yeah.
It's not. There's no special status to entanglement. That's the conclusion of the paper. As far as I read it.
Yeah, that is actually, you bring up a very good point, and maybe I should also revisit that paper and see what sorts of interpretations that I get from it. It's certainly true that entanglement is showing up in these algorithms that are decomposing superpositions into smaller states such as qubits, and the natural thing that occurs is your multi-qubit systems have entanglement. But I've certainly read a lot of accounts in the past that this isn't actually necessary in some moral way, because you could not be working with qubits, let's say, and then entanglement wouldn't really come in anyways.
Exactly.
So yeah,
they
it's a great point.
mentioned Gotsman, Neal, and other kind of things. The other quick comment is, for purity, I have colleagues from physics, and they have many definitions of purity. And some of them are, I think first easy to compute, I think. But the other thing is they have it's a real number, like how you can quantify purity. And I think that's the most important thing they do.
Right.
And I think that might be a good way to generalize this, maybe. So I have a notion of how much purity you
Absolutely. Yeah, I couldn't agree more. I think one of the inspirations for how this work got started was actually trying to take a more quantitative approach, where you actually take entanglement quantification, one of those metrics, and try to bake it into the system. Of course, that's immediately much harder to solve than the problem of simply asking whether something is entangled. But it sure is a very meaningful thing to do.
You can still have 0, 1/2, whatever.
Right.
A little bit entangled, lots of entangled.
Yeah.
Thanks. Could you go back to the slide where you had split in your program? Yeah, this one. Yeah. So one thing I'm curious about is obviously splitability or separability in general. It's hard to decide. Presumably we have to do some random computation. But maybe here, couldn't you produce some kind of a witness from previous operations that you could pass to split, to make it statically kind of feasible?
Yeah, that's a great idea. I think if you generalize that idea fully, you would, get some sort of reasonable static verification of the program. That's definitely something to think about. Yeah.
And also a comment. This purity analysis reminds me of some escape analysis used in programming languages. And tomorrow, there will be a talk about local mode notations, a new feature added to a camel compiler. And they do something similar. Basically, the annotations that let you reason about whether a value can escape out of the stack and go to heap somehow. And this reminds me of this as well.
Yes. I think along the same lines, there have been a lot of connections drawn in the existing literature between entanglement analysis and alias analysis of pointers. It's something very similar going on.
Okay, so I'll do one quick question and then I'll give back to Dominique. So could you show the chart again when you were measuring the overhead for the split?
Mm-hmm.
Yeah, so are you measuring wall clock time?
It is wall clock.
Okay. So I don't know how this iterated swap test works, but I assume that it does more samples of your circuit.
Right, yes.
So if you just counted the sample overhead, would you see something different?
It's a great question. So this is one of the shortcomings of our evaluation, which is we were only able to achieve it on classical simulation. If you were to do the similar kind of evaluation on hardware, then you would definitely need to take into account the number of samples you need and the precision with which you can actually bound your, hopefully a high confidence guess as to whether the thing is entangled or not. I think you would definitely be right that you might see in the worst case. I actually don't know exactly what the scaling law is. I'd have to look back at the literature, but in the literature of the iterated swap test, they actually give you, I think, something along the lines of confidence intervals for how many samples you would need. I don't have a better answer to that, though, unfortunately.
Okay. I think.
Are you aware of the quantum Hall logic with ghost variable paper?
Mm-hmm.
Because that one also has a logic where you can reason about entanglement. Of course, it doesn't come with the with all this automation and so on. But
Right.
I don't know. I mean, that one has this different notion of entanglement. So I wonder whether it could be somehow.
Yeah, it's something I've thought
Whether it's
about
relevant or
on
not.
and off. I've definitely read that work, and I don't know. I feel like taking some guesses here. If we were to try to extend the static reasoning of this system, it definitely makes sense to incorporate something like those variables. We did try to go in a radically different direction here with regards to like the single thing that we know how to check at runtime is not going to give you that much information necessarily, but tell you something.
Okay, last question.
Hi, I just got a question on your final teleportation program because do you have another definition of that that's not based upon the conditional measurements? Because I feel like if I was to use for instance, I could replace the Z with an X operator and I would still be able to end up with possibly a buggy program, but that's pure.
Right. So, well, there are two questions in there. The first is if there's a different way of phrasing it from the conditional measurement. Is that what you said?
Or just another way of going about it is what I'm wondering, because I'm wondering if the conditional measurements, then applying the operation, that kind of still leads it in a pure state, but you could potentially have an incorrect state.
Well, I don't know about other ways of writing the program. I will try to answer the second part, which is, can you still wind up with an incorrect state that is nevertheless pure? Absolutely, right? Purity is not, it's not a direct, what's the word? It doesn't directly imply a correctness of the whole program, right? To actually be convinced that the program does exactly the thing that you expect it to, you would need that. You could think of it more as a sanity check to actually tell you, I really would like for this value to be pure, and a lot of the bugs that you would encounter in hastily written quantum programs, I guess, are going to violate purity specifications and also safety specifications.
It's like showing that pointers will not dereference unallocated memory and so on.
Yes, something like that.
Okay, so let's thank Charles once again for his talk.